Well, it's time to start. This is a session on quantum calculations and quantum simulations. My name is Andrei Derevyanko. I'm from the University of Nevada, Reno, and I will be chairing this session. The first speaker of the session is Rainer Blatt, and he will be talking about quantum computations and quantum simulations with trapped calcium ions. Please.
Thank you very much. Good afternoon, everybody. First of all, I would like to thank the organizers for inviting me. It's a real pleasure being here. Thanks so much. And I would like to share with you a few of the things that we did over the last few years. This is work with trapped ions that we performed in this ion trap right here. And this is about quantum computations and quantum simulations with trapped calcium ions. The menu is going to be the following. I would like to introduce you first to some toolbox operations that we generally use when we do quantum information processing with ions. I will briefly mention a little bit more work in a more general way, what's going on in quantum computation with ions around the globe. And I would like to convey then, say, 4 different topics, 2 on scalability, that's of scalability towards quantum computing, and 2 about simulations. So I would like to show you how this scalability can be reached by quantum networks and how scalability is then done by usually encoding things in a logical quantum bit. And finally, I would like to share with you 2 experiments, how we do quantum simulations, both in an analog and a digital fashion. All the work is done at the University of Innsbruck in conjunction with the Institute for Quantum Optics and Quantum Information at Innsbruck of the Austrian Academy of Sciences. So let's get started. The workhorse, as you've seen on the first slide, is this linear ion trap, where we have the ions located in the string in the center here, and we shine laser lights to them, to the cooling and the optical detection, as indicated here with the CCD camera. But also we have laser lights that addresses individual ions to do the information processing. And we routinely see strings of about 15 to 20 ions, so this is a very typical result that we have, where we use either a few of them or all of them for quantum information processing. The more the status quo of the calcium ion trap quantum computer is listed here if you want to have more details. The system at hand in calcium is a 2-level system that we use for encoding the qubit between the S1 ground state and the D5 excited state. So that would be, in the pseudo-spin notation, a spin down. This would be the spin up state. And of course, we have a way of detecting things by shelving. That is to say, we just project the system, and if the system is down the ground state, then of course it scatters light. If it's shelved in the excited state, then of course it cannot scatter light because we have only a single line there. So this is the measurement that we do. But of course, our system that we denote as up and down in spin notation, or logical 0 for technical reasons in the up, and logical 1 in the down state, that of course is residing in an ion trap. And this notation is then the typical harmonic oscillator notation, so we note that we notate the states, just ordinary harmonic oscillator numbers. And with this, one is able to really perform universal quantum computation. Then you have the right set of operations. For example, if you have single qubit operations, arbitrary single operations, and 2 qubit operations of the C0 type, and then you can realize what's known as the so-called C0 circuit type quantum computer, where you implement universal quantum computation by the right sequence of single qubit and 2 qubit C0 gate operations. Over the last, say, 5 to 10 years, we have developed, and the community has developed sequences where we operate with more complicated gates, so-called Mellmer-Sørensen gate operations, and also collective operations it's a collective beam that we apply to the system, but does local operations and really address local operations. This is an overcomplete set, and I'll come back to that in a minute. And with this, you can actually realize then arbitrary operations, and this is usually broken down to carrier and sideband transitions with a radio frequency modulated laser beams, for example, and we analyze the system by measuring probabilities for finding these states in the respective excited states. And of course, prior to making these measurements, we rotate the Bloch spheres respectively, and then we get the tomography result. This is the typical fingerprint that we get then for a belt state. And sometimes in a spectroscopic notation, we do parity oscillations. I would like to point out that over the last 10 years, the number of groups working with single trapped ions really has really exploded. This is, to my knowledge, a fairly complete list, and if you find yourself not on the list, let me know. We keep a tab, and this is the latest list that we have on our homepage. And we will see many contributions here on this conference, especially many posters on Thursday. All of the locations listed in red have contributions to show on Thursday. So I would ask you to look at these posters then. And for this purpose of the talk, I've just listed here the locations that we have seen over the last 2 or 3 years now, fidelities for single qubit operations which are larger than 99%, and for 2 qubit fidelities which are larger than 98%. And you see, this is already 15, 16 groups worldwide that have these operations available, and there you can actually do quantum computing with trapped ions and also quantum simulations. And again, if you really want to know more details, we keep a running tab on our homepage, and if you feel you should be there, let me know. With this, I would like to show you some highlights from other groups that have come out over the last 2 years, especially the group of Dave Vineland at NIST and Didi Leibfried. They have shown superior gate fidelities right now, especially for the so-called Mermer-Sørensen gate operation, which usually takes about several 10 microseconds here. They have an infidelity of only 8 times 10 to the minus 4. This is one of the very best fidelities that we have. Then the infidelity for single qubit operations is about 3.7 times 10 to the minus 5. And they have really demonstrated recently everything in a scalable high fidelity architecture in one setup, which I think is a good starting point to do these things. Likewise, in the Oxford group, we have available now in so-called microwave-driven quantum logic atomic clock qubits. This is the system that's used by David Alcock and others there with these fidelities. So you get superior fidelities. You still have some limitations for these things, but they're really good and very good starting points to do this. This is just for 2 qubits at this time, and this is an Innsbruck-style trap. This is the optically driven quantum logic, also some of the very best fidelities that we have worldwide. With this, we can actually turn now to some of the computations and simulations that we have done. Let me return to the calcium. We have very similar fidelities, not quite as high, but we're working on that, and steady improvements are possible. But we are working mostly then with more ions, and we are trying to realize these algorithms for quantum computing and for quantum simulations. So let's start with the system again. The toolbox I've briefly mentioned consists of the entangling operation of the Mermer-Sørensen type, which is a 2-photon transition that we do here. And if you write down this notation, say for 2 ions in the ground state and excited state, and you have the intermediately excited states right here, which incorporate all the vibrational modes, then you see that these 4 pathways can interfere, and they can conspire in such a way that you get the superposition of both ions in the ground state, both ions in the excited state, and that's exactly what then leads to the belt states. That's the entangling operation using bichromatic excitation. The global, yet collectively applied local operations, this is a beam that hits all of them, but does a resonant manipulation right here. So it's just the rotations about the S and Y axis. That's why this notation is a shorthand notation for that. And the off-resonant notation here, the off-resonant excitation, that's usually used by Stark shifts. That's why we denote it as sigma C. And this is the unitary operations that pertain to all of these operations that we write down. Again, local Stark shifts, collective yet local operations, and then the entangling Mermer-Sørensen operation, which is a spin-spin interaction. And of course, depending on the phases that you apply, this can be pretty general. In addition to that, and I won't have the time to go through all the details of that, we have so-called hiding operations in order to reduce or enlarge the computational subspace. We can use dephasing operations in order to simulate open systems. We, of course, have initialization and reset operations, and we even have a quantum cache memory with a lifetime of about a few milliseconds. With this, we can then really have to find a sequence of all of these operations that do the algorithm at hand. So we have developed over the last years a so-called quantum compiler that breaks down the algorithm that you really want to implement in the required unitary operation. In order to do that, what we have come up with, we just start then for certain routines with a bunch of local operations, and if we can't get the unitary that we require to do, then we add one entangling operation and another set of local operations, and then try to see that this converges and find the right unitary. If it doesn't converge, we add the second layer and so forth. And this can really be efficiently implemented for a relatively huge set of subroutines, and that's how we bootstrap the entire system. So we develop these routines and then have these operations as basic operations available in our toolbox. And with this, we could implement, for example, a full-blown show algorithm and show that it's scalable. So if you really want to see that we can actually do a quantum multiplication, this is the truth table of such a system. So you just input here your number and they read off, for instance, the result like that. We can just multiply by any number that we have here in the system, as long as system length is there, and you find more details here. And this, the system, the compiler, for example, allows you then to really break down any operation that you need in order to realize these computations, like, for instance, this Fredkin gate, it's a controlled swap operation, in a bunch of pulses. Just getting these pulses, that doesn't tell you very much, because you would have to do some reverse engineering to see what the underlying routine is. But this is what the compiler finds, and we have optimized this, so this is what we usually use then as a Fredkin gate. Likewise, if you really require more complicated results, like complicated routines like this for controlled NOT operation, this can be relatively easy implemented, but it's not easy to see this right away. If you really do this subsequently with entangling operations, it's fairly complicated. But again, this is all available now, and this is now the underlying operations when we do quantum computations. So let's just try to think about the toolbox operations if you need to scale things up. For scaling things up, one could think about quantum networks. And for quantum networks, you need interfaces. Interfaces could be done by using cavity QED. So you have an ion right here, and you have a cavity. So the ions serve as the quantum memories, and the cavity serves as the interface, and the optical fiber here would serve as the photonic channel, as we've seen this paper by Ignacio, Peter, and Jeff Kimball and Hideo Noguchi a long time ago. And the realization of a quantum internet could be envisioned as was done by Jeff Kimball in this paper. What has been achieved in the meantime, we have seen that remote ion-ion entanglement is doable over longer distances. This is work by the Monroe group some time ago. Teleportation between remote atoms can be done, work by the Rempe group, and direct state mapping has been done by our group. Let me just give you a few ideas how this is realized. And if you want to know more, just talk to Tracy Northup, who is here, and also has a poster on Thursday. So we have in our group typically ions sitting in the trap, and they are sitting in the center of such a cavity, and this is the outgoing photon right there. And for example, we can use then a bichromatic light field to create entanglement. For example, we take a Raman transition to create, say, a horizontally polarized photon right there, like that. But of course, with a different detuning, we can also create a vertically polarized detuning, the bichromatic light field. And so we just generate with that ion photon entanglement, which of course can be very generally steered by using the Raman conditions which go into these beams. And then we have a very general way of doing, of entangling the outgoing photon with the internal state. And to make a long story short, if you really want to know the results, you see the fidelities for, say, this ion photon entanglement can be relatively high, 97, 98%. And there's a big variation of Clauser-Horn-Szymanyi-Holt inequality. And with the same procedure, you can actually do the quantum state mapping by just shining into laser beams, for instance, which are then resonant to these ground state transitions. So you have the qubit encoded in S and S prime. Then you shine in respective laser beams, and you create then the superposition of the horizontally and vertically polarized light in such a way. The fidelity is slightly less, but that's doable, and the details you find here. So these are the tools that are necessary in order to create entanglement in a remote fashion. And this can even be heralded by doing this twice. So you just take two ions in the cavity, for example, indicated by this, and you just write down the same state that I've done before, and do this with ion number 1 and ion number 2. And then the output then is a photon, and it could be two photons, and you see there's a vertically polarized photon and a horizontally polarized photon. But there are more outputs possible. Whenever there are two horizontally or two vertically polarized photons, and the respective states you don't care. But once you have a coincidence measurement of horizontally and vertically polarized photon, then you know that you have an entangled state left in the cavity. So all these tools are available, and this works again with a fidelity which is 92% in this case, and one has to make sure that this is optimized, of course, for the respective lifetime, for the time to detect between these photons, and the repetition rate at this time is limited. So this can be enhanced, and this needs to be enhanced to be practical. And here's another way of using then collective ion cavity couplings to enhance this. This is a quantum interface. If you just encode a qubit in a more collective state, then you get the enhanced coupling rate. So for example, when you take two ions, that's the simplest way to do that, and you superimpose them in a super-radiant or a sub-radiant state, or a supercoupled and subcoupled state in the cavity, then you can show, when you just look at that, this gives you enhancement or suppressed emission in the respective states, and so you can, for instance, when you tune it at this point, enhance the rate at which you really see then the photons getting out of the cavity. So there's many points to play with by using these entanglement protocols, and then even to use quantum optical protocols to enhance the rates with that. The next thing, if you really want to scale the system up to larger systems, is that you have to make sure that your gates are protected, that your qubits are protected, and that all operations are corrected for. And if you have this this two-level system as a qubit, then, for example, protection really means that you go, for example, to the so-called decoherence-free subspaces. In such a case, one would expect that you see sort of a dephasing with respect to magnetic fields if you're, for instance, in the semi-sensitive qubit transition in the calcium. But if you encode this in the singlet state, this belt state, then you see then the respective shifts are symmetric with respect to the state right here, and then the decay of that belt state is only given by the excited state lifetime. There's no dephasing. Look at the time right here. This is 1 second lifetime. This is what we call a decoherence-free subspace, and depending on what you have there, you can create those protected states. The more active way of avoiding these errors or just undoing these errors is error correction. And for this, you need to first measure the error syndrome. You have to encode this in a redundant way, measure the error syndrome, and then do the correcting procedure. All of these things have been done in the lab, but in order to make this more reliable, you need more and more redundancy. And more redundancy requires that you have more qubits in order to encode a logical qubit. And this is the next step that I would like to show you. And what we have done, what we've seen over the last years, that we can really use, say, a larger number of physical qubits to encode the system in a topological way. And this is research was guided experimentally by Thomas Mons in our laboratory and theoretically by Markus Müller. And let me just briefly tell you what that is. What do we mean by topological code? The information, if you encode this in the right way, for example, that this is a cup and this is a donut, is essentially the same because this is one whole. So the topology of the cup and the donut is the same. If you encode the information in your system in such a way that local noise really is, that the noise and errors are only local, then it doesn't matter because you're looking then for the global feature, which is that whole, that topology, in order to protect the system. That's the idea behind it. And now what are topological color codes? The idea is that we keep the colors here essentially only for bookkeeping, but we want to have stabilizer quantum error correcting codes, which really means we put the qubits on the vertices. Each vertex is supposed to hold a qubit right here, and then we define X and C type plaquette stabilizer operators, which define the code space by going around these plaquettes and doing the right measurements. This is, by the way, for the connoisseurs and the people who know more detailed CSS code, that is, we can independently detect and correct a bit and a phase flip errors. Topological protection, as said before, works, of course, in this case only if the noise and the errors only act locally. So if you just have a global error right here, then of course this would not work. And one can show that logical operators, like this logical C operation, is then a string in this direction, and other operators would be other strings. This was figured out by Hector Bombin and Miguel Ángel Martín Delgado already some time ago. The question is, why the heck do we want to do that at all? The reason for that is simply that with this kind of redundancy that you get there, that you get higher error thresholds. And so we expect to see error thresholds of about 0.1 to about 1% versus the 10 to minus 5 that you have here for concatenated codes. So we expect these codes to be less sensitive with respect to errors and easier to correct for. Let me just give you an idea how this works. This is the minimal instance of that, so there's 7 ions right here that we have. So we have 3 plaquettes, and these are 6 stabilizers, so essentially we can encode 1 qubit. And encoding really means we prepare the system first in +1 eigenstate, so we use a nearly decoherence-free subspace, that's a staggered state, and that fulfills these requirements, and then we go plaquette-wise around and just do the entanglement for the X operations. Entanglement really means we are just considering the red plaquette, then the blue, and then the green, for example. We do this by hiding, for example, these 3 ions right here, and then make a global entangling operation. Then we unhide these, hide these 2, make a global entangling operation right there, and so forth. And in total then, after applying all of these gate operations, we have encoded our logical 0, for example. That is the logical encoding procedure. That is quite expensive. It takes about 100 gate operations to do that. On the other hand, we expect to be able then to do error correction. Let me just show you how this is initialized and how the code space looks like. If after the first step, we see these 2 states are carrying the information. These are the stabilizer codes. This is the logical qubit right here. Then after the second plaquette, we have 4 states that are used for the encoding. And finally, after the third step, it's 8 out of the 2 to 7 states that we have right here. So this is digital notation that really hold the information. And now comes the good part. Stabilizers have a +1 eigenvalue. So we just check whether these eigenvalues are +1. So for example, we just take the X stabilizers right here. If everything is +1, we have no error, we're happy. But once we see a -1 right here, we conclude if there's a -1 here, there must have been a phase flip on ion number 7. If that's -1 right here, it must have been on ion number 5, and so forth. You can go through this table, and you can uniquely identify where the error was. Once you have identified where the error was, of course, you can go back and point the laser beam there, and then really undo the error. And this is shown here experimentally how it works. This is how we find the stabilizers then, and this is the logical qubit. If you produce an error on 5, then we see that stabilizer is flipped. If you produce an error on number 2, then of course these 2 stabilizers, the pertaining stabilizers, are flipped, or in ion number 3, then all of them are flipped. And so forth, you can go through that, and this can be shown to be able to correct an arbitrary error. And the question really is, why do we go through such a code? There are other codes like the Kitaev surface code that might even be a little better what the error threshold is concerned. The reason that we have chosen the color code is simply that this has a property which is called transversality. Transversality means the following. When you now want to make a global operation, say a Hadamard operation or any other logical operation on your logical qubit, then depending on the way you have encoded that, it could be a very complicated operation like a CNOT gate or whatever you really want to do. Transversality then means if you have a code which is transversal, then this breaks down to making these things locally in such a way. So in other words, if I do use now more redundancy, going for a 12 or a 17 qubit color code, then I could simply make the Hadamards individually. And this really makes life easier when you go to larger architectures or when you go to more redundancy. And my vision of having a scalable quantum computer would be then such a way you just encode logically a logical qubit in one string. Of course, you need some ancillas to do that, and the second one, third one, and so forth. And then the transversal operations would be then available to make all of these interactions between the logical qubits. That would be the vision behind this. Let's just see whether we can do these logical operations. And when we just use now 7 qubit, then the 7 qubit C operation, X operations are written down. As indicated here, we have the Hadamard, the K-gate, and these are the respective matrices. They can all be done, the so-called Clifford gate set. This is not belonging to the Clifford gate set, but this is necessary to make a universal quantum computer with so-called T-gate. For this, we would need an 8th ion of so-called gate injection. that doesn't really matter, but this can be done. We know how to do that. Let me just briefly show you what we have been doing and how well you can do that. If you just take now this as a block sphere, which denotes the logical qubit, so this would be the 1 logical and the 0 logical, then we encode things, and then you apply, say, an X operation. And you do this by doing this in a transversal way to each one individually. Then you see exactly what it does. It makes a spin flip as supposed. And likewise, the Hadamard makes a superposition, and so forth. And when you just go through the truth table, you see that this works within the code space with high fidelity, close to the 90%. That's fine, but it does work with the code space on average. What we would have to do in order to make now the full error correction is to make this in a single shot. This is where we are working right now. Once we have the availability to get this in a single shot measurement, then we can go through all of these things and, of course, kind of make a full correction. And of course, once you have that, this is a code that can be applied to very general architectures. This is what we are trying to do in Innsbruck. It's a 2D architecture. These traps are at this time in the lab, and we are working on them. But you could also use it for solid-state platforms, for atom platforms like Antoine Probet's platform. This is the atomic platform of Mark Safman, or the ion platform in John Bollinger's group. So much for the progress on quantum computations. Let me now turn to the simulations. In simulations, we are usually distinguishing between analog and digital simulators in the quantum simulation way. And the goal is always to simulate the physics of a quantum system of interest by another system that's easier to control and to measure. The approach here for the analog quantum system is now in such a way that we just take our system and we try to embed or emulate the system to be simulated by reinterpreting the parameters that are underlying. We have seen such things already when you just looked at the optical lattices. So for instance, you want to see the phase transition between the superfluid phase and the Mott insulator phase, the ultra-cold atoms and optical lattices. This is typically what you can get. Or we have done similar things, and I'll show you another experiment of us with ion crystals, and Chris Monroe is probably going to show you more about this. These experiments have been done studying quantum magnetism in spin chains. So let's see how we do this. This is work in our group, which is guided by Christian Rosa and Ben Lanyon, and this quantum simulations with spin chains, where we use now transverse excitations, which really means we are using the gate in a transversal way. This is a technical detail, which is fortuitous in this case. And otherwise, we are just using the string, the ion string, as a spin chain. So let's take the spin chain, in this case 7 ions. And what we really want now to realize is, if you want to simulate, say, is an Ising model with a spin-spin interaction here and the interaction with the transverse magnetic field. One can show, this was shown also by the Monroe group some time ago, that you can actually encode that in such a way that this is an approximate power law dependence. And we can just change these things from infinite range interactions by using the center of mass motion, they're infinitely there, or to dipole-dipole interactions which are closer, almost nearest neighbor, not quite. We cannot go to directly nearest neighbor interactions. We are interested here in this case in a particular case where this B field is bigger than the Jij matrices, so this can be rewritten in the so-called Hartz-Hoping boson model, but that's a detail. Let me just show you what we try to investigate. For this, we initialize the ions first in the spin chain, and we just want to investigate what is the interaction strength between the two ions that's measuring the Jij matrix. So we just hide, say, all of the other ions. We just single out I and J, then invert that one, and then, for instance, let the Ising-Hamiltonian go and see what the evolution of the system is. And from the time evolution, we can actually see the energies in the system and can reconstruct our Jij matrix. And here's the Jij coupling matrix as a function of the spin that we have here. And you see this is, of course, strongest with the next neighbor, but then it trails off. And if you just look now at the dispersion relation as a function of the momentum right here, see the power law dependence, these are the circles, and the experimental data that we get from there, they fit very nicely. So this can be nicely done and corroborates that what I've written before. What we investigate with that is so-called quasi-particle dynamics following a quench. So we just quench the system by inverting a spin right here, apply then the Ising-Hamiltonian, and then let the system go and how it evolves in time. This is time going up, there, and we see the time slices. Then you see that the magnetization spreads out, and it gets reflected right here. There's interference happening. So we can study a myriad of things. For instance, we can have the inversion right here and see how this is spreading out there and reflected, or we can even have, say, two quinches to the left and the right and see the interaction. Or we can study correlation functions. That's, by the way, something that was studied in more detail by the group of Chris Monroe in this paper, and maybe he will talk about this later on. So these are the kind of investigations that you can make. You can see how the magnetization evolves in such a spin chain. And what we have investigated in more detail is how this behaves if we change the interaction range. And if you have a short range interaction, which is not quite nearest neighbor, that what you would expect then from nearest neighbor is the so-called Lieb-Robinson bound. This would be the white light cone behavior right here, whereas what we actually see is already here, which is not quite nearest neighbor, that we see the magnetization appear already earlier. And the more long range interactions we have, then of course, the earlier this gets, the system gets entangled. I do not have much time to go into this in more detail. I would rather like to go on and give you, in the last, say, 10 minutes, some newer results that we have obtained now with digital quantum simulations. A digital quantum simulation is also known as a universal quantum simulator, because in the end, what you're using is a full-blown quantum computer to actually do this. Again, this is research carried out by Christian Roos, Thomas Mons, and Ben Lanny in our lab. And again, we used our ions now with as a quantum register, and we use the global operations and the local operations as before as a full-blown quantum computer. And the idea is essentially now to realize this in a circuit model where we replace every interaction by all of these unitaries. But when you have the system at hand that you really want to simulate, then of course this is not easily implementable, because it could very well be that the underlying Hamiltonian is to be written in a sequence like that, and then do not necessarily commute with each other. Then you would either have to go to the Hausburg-Baker-Campbell formula and do the calculation, but then you have done your work already. Or if you cannot do that, then you implement that in such a way, an approximate way, the so-called Trata Suzuki approximation. So you just apply this Hamiltonian in a unitary fashion for a time slice, and then repeat the sequence n times. This is known as the Trata Suzuki approximation. So let me just give you a short example how this works. So we just take our degrees of freedom, and we take this as the Hamiltonian, and we really implement each unitary. That's the unitary that we actually use then with a laser to implement the operation on the ion string. And then we approximate this in such a way that we apply this unitary, that next one, next one, next one, only for a time slice, then do that sequence n time. In the pictorial way, we see this as a circuit that's applied only for a short amount of time, and then we repeat this sequence. This is what we call one Trotta step. And that, in the end, should give us the time evolution in an approximate way for the full system. That this is efficient for local quantum system was shown by Seth Lloyd in this paper some time ago. As a proof of principle demonstration, just to give you an idea, the flavor how this works. This is, for instance, again, our Ising system. So it's our spin-spin interaction. This is the interaction with transverse magnetic field. And you see immediately, this can be recast in a Milner-Sørensen gate operation. This is recast by our Stark gate operations. And now we have to apply them only for a short amount of time. And for example, when you want to calculate how often we see in a two-spin system, how often this points up or points down, then that's exactly what we probably expect to see. So let's try to do that. We mimic that system in a full-blown time evolution by switching back and forth, say twice, and to see that the agreement between the experimental data and what we expect theoretically is lousy. That's the fidelity that we get overall. And that could be improved, of course, by going to finer time slices. It's already getting better, and the fidelity is 85%. If you go a factor of 2 further, then of course this gets even better. It's 91%. And another factor of 2 doesn't get us better fidelity. And here we see already where the errors come in. The reason for that is now that we have to use so many individual gate operations that the individual fidelity of the gate operations is not sufficient to keep this going. On the other hand, one knows what the errors are in the so-called Trata Suzuki approximation, and again, one could apply, in principle, after each step, a full-blown error-correcting phase, and that would give you then a real-time evolution which is error-free. This is why this is called a universal quantum simulator, and this is the advantage of this as opposed to the analog quantum simulation. So let me just show you in the last few minutes what we have done with that. And this is a fairly new result. That was work that we did together with the theory group of Peter Zoller. And this work was guided experimentally by Esteban Martinez in my group and Christina Muschig from Peter Zoller's group. And what we really tried to do and to demonstrate was the first application of this Trata Suzuki approximation in a full-blown quantum simulation to calculate a result that's a bit more interesting. A bit more interesting because we really want to go to the realm where we really are able to eventually do calculations that cannot so easily be done on a classical computer. So the idea is to quantum simulate lattice gauge theories. The idea would be to have a quantum electrodynamics in one dimension on a lattice. And what we are considering here are particles, in this case fermions, as the encoded spins. That's, again, our two-level systems of the ions. And the idea is, and this was done by the theorists, they use the gauge field formulation and they transform it in such a way that they rewrite it in long-range interactions and hand us down the Hamiltonian, which then consists of the Pauli operators that we can implement. And then the idea is that we use these Hamiltonians and make these interactions and simulate it stroboscopically in a trotterized version. The idea is really to simulate now the following process, the Schwinger model. That is to say we just want to create a pair of particle-antiparticles and to see how this process dynamically evolves. And this is done in a very simple version with just 4 ions at this time. So let me just show you what we do. Again, the basic idea is to get to a very sophisticated encoding. The encoding is key to make these things simple. So let's look at this in more details. We encode this in an elegant way, fermions and electrons and holes into level systems, as we expect that to do. But we now also make use of the fact that we have access to the individual sites, so we can number the sites. This is an odd and even site, an odd and even site. So when we say, okay, all the odd sites can only contain electrons, and the even sites contain the positrons. And if the system is in its down state, then that's supposed to be an electron. If it's in the up state, it's supposed to be a hole, and because that's on this side. But it's on the even side, then it's down, that's a hole here with a containing positron, and if it's up, then it's an electron. Sounds sophisticated. We could have gone this in a different way, but this is really making this system simpler. So the Hilbert space, and this is now getting clearer, consists of the notation vacuum, particle, antiparticle. The Hilbert space that we have with these four particles is such that we call this the vacuum, and then there's these different states available. And whenever something is going beyond that, of course we can post-select the entire system, then we say this is unphysical, we do not consider such a transition. In the end, what we really want to consider is the transition from the vacuum to the state where we create that pair. So that's the pair creation process that we investigate. Now, what's handed down to us by the theorists is, of course, a rewritten theory from a lattice gauge theory in such a way that they just encode these things in the interactions. So we get an effective long-range interaction. We get the particle-antiparticle creation, annihilation, and of course from the transformation you get what's called the effective particle masses. But you see all of these things suddenly appear now in ways with Paulis that can be easily implemented, in quotation marks, easily implemented in our system. That really makes it doable. So we have here the fermion light coupling constant, lattice spacing, and the particle mass. And now the point simply is we have to implement these coupling constants, this coupling constant, and this, so this is a bit more complicated. If you just look at it in more detail, you see it's asymmetric, and this is exactly what you have to tailor into your simulation. And this can be done in such a way that we now take, again, our trotter slices. So we have this part where we have these CIJs that couple the CC part, and the plus minus the hopping part, and the effective masses. And if you just take this again, this is implemented with asymmetric Schmelmer-Sørensen that we apply here to get this trailing off interaction, and then you're done. But that's, of course, a step-by-step system that you really do. And in order to prepare the system in the vacuum, we have an initialization pulse. Then we have this sequence that does this sequence of these pulses, these time slices. But for the throttlization, we have to apply this, in this case, 4 times. And then we have a trailing pulse in order to make the measurement. In total, that sequence is about 222 gate operations, where we have also some calibration pulses that are necessary to keep the system really where we really want to have it. So this is one of the most complicated quantum simulations that we have been able to do, and let me just show you the result. What you see here is the particle number density, where 0.5 really means it's about 1 pair. So that's the particle density, that's the definition right here. The ideal evolution, which you still can calculate for this 1D system, is the green curve. That's what you would expect. What we get experimentally are these experimental data. This is the experimental error model. If we assume we have just a phase error right here, then we get that. And the discretization errors from the Trotter model are written here. The chairman's already up there. Let me just finish this. What you start out, this is the vacuum state, and what you create here is just a pair. This would be the pair creation process that we study. Of course, you can do that now, and you can vary the parameters. This is the line that I've shown you here. So you can take the mass as a parameter, the interaction as a parameter. This is something you calculate. This agrees nicely with these things. And let me just finish with this. You can now consider also so-called vacuum persistence. You see, the vacuum decays. How well does the vacuum persist as a function of the parameters? And more importantly, you can also measure, because we have access to these particles right now, how much they are still entangled, because they you create a particle right here and a positron and an electron right there. Of course, they have interacted and they are entangled, and the entanglement can be calculated from the negativity right here. You find all the results right here and more of the theory, how this is done. But it shows you that we can actually do these simulations in a quite an interesting way, and we hope, of course, to get to even more complicated systems. With that, let me just finish here. We have shown you that we have this toolbox available. Of course, we want to go to further simulations and to make things better. We already have in the lab a structure of more than 50 ions. We can at this time control the innermost 20 to any arbitrary degree of freedom as much as we can. But of course, we want to get to better detection and do lots of these things. But most importantly, what we really need to do over the next years is what I call keep the qubit alive. This is not to be confused with an eternal qubit or an immortal qubit, as some people would like to coin it. It is just keeping the qubit alive for the time of your calculation. The rest, I don't care. But I keep it alive for the time of the calculation and keep the coherence alive. Once you've done that, that's a new project that we have just now, then you can do the rest, and these things are working out. This, of course, was not done by me, but by a large team. And of course, with the theory support of many people, of the Zoller group and the group of Martin Delgado. And here are the names. With that, thank you very much for your attention.
Thank you for an interesting talk. We have time for a couple of questions, please.
Good.
So you showed a picture of a 2D ion trap.
Yes.
The ions were maybe 100 microns apart.
Yes.
How do they couple?
They would couple via double-double interaction. The question is really, I showed briefly the picture of a 2D ion trap where the ion is an array of 4 by 4. At this time, the ions are about 100 microns apart, which is too big. We have to go down to an ion distance of about 50 microns. That's the next generation of the traps. Then we get a coupling of in the order of about 10 kilohertz. And that's the next generation of the traps that we are doing. This would be the way of doing it. And then this double-double coupling, as we had shown before.
Okay, since we don't have any more questions, let's move to the next speaker.
There you go. Just take it.
So the next speaker is Chris Monroe from University of Maryland.